Hi, and welcome to our new session here in our chapter on risk minimization. So this is the first session where we are going to take a deeper look into classification and classification losses. So I will introduce a couple of general formulas here for, risk computation in classification, and we'll specifically also look at the 0-1 loss, which is probably one of the most, well-known loss functions for classification. We'll discuss its advantages and disadvantages. I'll derive the risk minimizer, so the optimal predictions, constants, unconditionally and conditionally. We'll talk about what the base error rate is. That's pretty much the associated theoretical risk value under 0-1 loss. And I'll wrap up by showing a very, very short and very simple simulation example to demonstrate the base error rate, where that example will also give us a short chance to discuss generative approaches in classification, because that is how I constructed this here. Okay, let's start. So we're going to take a look at hard label classifiers here. So we have a discrete classifier. I guess I usually call this a hard labeler, as our notation for that is an H for hard labels. I just need a different symbol and not an F, and it maps from our feature space to our discrete and finite label space Y. So here I'll sometimes take a look at multi-class classification as well, but very often we'll discuss binary classification, so 0-1 encoded labels or -1 + 1 encoded labels. Now, one of the most natural loss functions one could associate with such a classification system is the 0-1 loss. What is the 0-1 loss? So here is a complicated way of writing the fact that we are simply counting how often we are wrong. So as our loss function, it takes a true label Y, and it takes a prediction. In this case, a prediction is also a hard label. So we just compare the two. If they are correct, loss will be 0. If they are incorrect, then loss will be 1. And at the end, as always, we sum this up or we average that, giving rise to a risk value. Now, if we have labels which are encoded as a -1 and +1, and if we use a scoring classifier, so something that outputs a value on the real line from -infinity to +infinity, as we've discussed before, very often it is nice then to write the loss function in terms of the margin. So the margin is just Y times F. So this gives us a signed value. If this signed value is positive, then we're pretty much predicting the correct label from our score, assuming we would threshold at 0. And if the sign is negative, well, I guess then we would have produced the wrong label. And the confidence score of the F is still, maintained, so to speak, in this margin value. And the nice thing is that using the margin, we can now plot our loss function in a single argument and not two. We have done this here, I've discussed this before, and you can also see how the 0-1 loss function looks like. That's the area here where, assuming again we would be thresholding at 0, which would be our default for such a decision score-based classifier, we have a loss of 0 because we're producing the correct sign, so to speak. In here we have the area of the incorrect predictions. Maybe I should mark rather the x-axis, so to speak, the margin axis. You can now write it like that. So that's just the indicator function evaluated on the margin, or like that. I guess it's just plugging in the definition of the margin. And if you really want to, or for completeness sake, I'm now also writing down here the case of 0-1 encoded labels and a probabilistic classifier. So this we would naturally threshold at 0.5. And there is, there are many less convenient ways of writing that. So I'm not going to read out this formula, but this here produces the same thing. And this is pretty much a direct translation of the probability to a threshold to a decision score now thresholded at 0. And this here recodes our -1 + 1 labels to 0-1. So usually these things are not necessary. I just want to do this here for completeness sake. what is a little bit more, and you, I don't know, can maybe look at this for a few seconds and check out that this is actually correct what I'm saying here on the slides. At least I very much hope so. What's a little bit more interesting is considering whether, yeah, I don't know, this is a good loss function or not. Maybe in terms of hardness of the optimization problem, usually we go through these analytic properties of these loss functions and we discuss them a little bit. I've already said it seems quite natural, right? Just counting misclassification errors. I guess if there would be like a certain costs, misclassification costs associated with the task, maybe you would like to learn based on these. I'm not going to, I don't know, assume this here, so I'll assume that the loss function is maybe indeed, I don't know, we don't have extra information that kind of violates the reasonableness of this loss here, okay? So we have two classes, we have maybe G classes, we don't know about any costs, and classes are maybe of roughly the same size. Then I guess counting misclassification errors might not be the weirdest thing ever. On the other hand, this loss function here, well, you can immediately see that this is not differentiable because it's not even continuous, and that makes it pretty hard to optimize. So even if you look at one of the simplest associated optimization problems, so you are just using a hypothesis space of linear functions, you can show that the resulting risk minimization optimization problem is already in NP hard, and that means that this is close to intractable for larger data. I guess for up to a certain size we can still do this. It's just at some point going to become terribly slow. For that reason, this is sometimes used for evaluation, this loss function. This is sometimes used for theoretical discussions as here, but very often this is not what you optimize in practice. If you're interested in more details on the proof of the NP hardness, I've, as always, linked a nice paper here. Okay, let's start out by deriving a few simple general formulas which will be useful later on. So many of these things are not only true for 0-1 loss, so I will use them also later in other sessions where we discuss other classification losses. So as we've done before, we're going to unravel now our theoretical risk formula here by applying the law of total expectation. So what is risk? Well, that's just expected loss, right? And we can do law of total expectation for this. We've done this before in the regression case, so this is nothing new. So the one thing we can now do here is we can recognize that our y is a categorical distribution. It's a random variable with a finite amount of values it can take. So we can just easily plug in the definition of that discrete expectation, and that's simply this here, right? So for y, we iterate through all potential values k it can take. This is just finitely many. And then we just have to plug in this guy here, which is the function on our random variable. And then we have to multiply each instance with the probability that y actually takes the value k. And then you also plug in the k here in this function, which is inside of the expectation. And I've done exactly that. Okay, so far so easy. That works with an arbitrary number of classes. Yeah. For the binary case, we can now derive a somewhat, I don't know, special formula, which is not that special or not that hard to see. It's just, I just want to use it as a starting point later on, and this is often what is also used in many papers. So I wanted to introduce this here. It's just convenient. So if you look at the case of binary classification and then you look at this inner part, well, it's binary classification, right? So there's just two cases now. So we have the case that y is actually a positive class, and I'm using a little abbreviation here because I also want to kind of have this I want to have a compact notation for these prior probabilities. For these in general for these probabilities here. So I'm using eta of x, maybe eta k of x so eta k of x would be the posterior probability that y takes the value k conditionally being at x. And yeah, in the binary case, I only need one eta, right? Because that's just the probability of y being positive and then the counter probability. And I can now take this formula here and look at the sum. It's just going to take two cases, y equals 1, y equals 0. So just write down these two components separately, and I multiply with the prior probability, which is here the one for y equals 1, and here is the one for y equals 0. Okay, maybe given x. Yeah, so we now have a nice convenient formula to remember to compute the expected loss, the theoretical risk for any loss function under binary classification. Okay, and this works pretty much for any loss. As I've said before, it also works for hard labelers, for hard labelers, decision scorers, or probabilistic classifiers. We can also maybe take a look at this formula above here, so maybe I don't have to delete this line. So what this basically tells us is that if we would have, so let's move a little bit away from 0-1 loss now. Like I said, this holds in general. So you could envision your loss function here. If it's hard labels, let's say there's like three classes, okay? 1, 2, and 3. 1, 2, and 3, and maybe this is y, and this is y hat. And then maybe for correct classification, which would be here on the diagonal, you would have costs of 0, and here you have some other arbitrary costs, right? So you usually would just have a 1 here for 0-1 loss, but maybe there's like different values. I have no idea. Let's just write in some really super random numbers. Okay, so this might be something like a cost matrix, right? Which looks really ugly when I'm writing it. So I'm keen on deleting it very quickly from the slide. For hard labelers and finite classes, I can like specify my loss function like that, right? But you can also call this a cost matrix. And what you can see is that this risk computation here is pretty much, if we would now minimize this, which I guess we are not looking at here yet. So it's just what would happen. So maybe this slide is not completely correct in that regard. So I guess we would have to take it one step further. But if you would now like minimize this here, yeah, in terms of like the decision you would take, which is exactly what we're going to do in a few minutes for 0-1 loss, and where you will see the result, and I will derive that. So if you would also do this for this here, you would see that you would look for the cost optimal decision under such a cost matrix, yeah, which is then weighted also by these posterior probabilities. The reason why I'm not doing this here is because, I guess there's a little dash here missing. There's a whole area in machine learning which is called cost-sensitive learning, which is also part of this lecture here in a later chapter, and we're going to look at this anyhow, and I don't want to do this now. So, okay, enough rambling about more complicated things. Let's really take a look at 0-1 loss now. So let's do this for multi-class and for hard labelers. And let's derive what our optimal predictions would be, as we've done this before for regression. So here I will take a look at things unconditionally. So I just want to compute the best constant prediction over my complete distribution. So what do I have to do for this? I have to use my formula from the slide before. And now I have to minimize this here over k, right? So that's just the inner part. This is exactly this thing here. Yeah, we now have to, well, we don't have to minimize it point-wise, we have to minimize it overall, but yeah, as I've said before, there's basically not a big difference in terms of how we are approaching it and how the solution works like. So we now have to look at what happens when we take a certain value k as a prediction. So k here is going to be our prediction. And then we iterate over all potential classes L in our label space. we compare K with the true label L, and we have to multiply this by the probability of the class being L. Now, what do we have to do next? This is true for any loss function, but here we are operating under 0,1 loss, right? And 0,1 loss tells us, well, this thing here, this is pretty much always 1. It's always 1 in case L does not coincide with K. Only if the two are equal, then it's 0. So we can just remove that case from the sum. And then we can see, well, we can also remove the L, because like in these other cases where K is actually not L, the loss function is 1. It is 0,1 loss after all. So we have to just multiply all of these probabilities here, yeah, of Y being L. So we sum them all up for K not being equal to L. And there's just this one guy missing of Y being K. So this is just a counter probability, right? And in terms of minimizing that, we can just maximize this guy here. So we maximize that, and that's our result. And that's a simple proof for a very, very natural and somewhat obvious fact that we're going to predict the most probable class. You can also do an empirical version of this. So you can, I don't know, if you want to theoretically prove this, either you're going to do this again empirically, or you just do the plug-in estimator, insert the empirical distribution. In any case, what you empirically have to do is you have to look at your training set. You have to compute proportions of classes. So these pi k head guys here, these would be just your empirical proportions of your classes. I don't know, maybe for class 1, 10%, class 2, it's 70%, class 3, let me make sure that this actually adds up to 1, so maybe that's 20%, and then you would predict this guy here. So class 2. And you can also do this conditionally. So this is what we actually call the risk minimizer or the base optimal classifier, and that would be at any point x tilde, you are predicting the most probable class again, but now with respect to the conditional distribution of Y being K, given that we are at point x. And I'm not going to prove that again, because the proof looks exactly as before. And we've discussed this connection between unconditional and conditional minimization before at length, I guess. What you can also do, and that's also not super difficult, I hope most of the things here in this short session are not too difficult, is you can just insert the result from before into our risk function. So we can ask ourselves the question, okay, if we're using now this base optimal classifier, what is its expected error rate, its associated risk value at the optimal model? So I'll just insert this thing here. That was our risk minimizer, right? So at every point x, we take the class which is most probable under this conditional distribution. And then I take the expected value of this thing. And that's the, well, what is that? That's pretty much the probability of us doing things correctly, right? So if we compute the counter probability of that, it's very obvious that, I guess you could maybe now invest this one extra line to formally show this, but I hope this is very obvious that this is, if we compute the counter probability of that, this is simply the percentage of cases where we incur a 1 loss under 0,1 loss, right? Where we produce the incorrect label. So if we are, I don't know, if we, maybe let's do one example. So maybe it's binary classification. Maybe the two conditional probabilities would look like that. So that would be class 0, that would be class 1, right? Well, like that. Which class would we predict? Well, the one that's most probable. That's the one with 70% error, right? So what error, what 0-1 loss are we going to incur if we make that prediction at that point? Well, obviously 30%, right? Because 30% of the time there would actually be a 0 label, but we would predict 1, so there's a 30% chance of us being wrong. And that's exactly what this formula above here says. It also just says that we, as always, we have to integrate that out of the whole feature space. So that's our base error rate. So we now have a nice little formula for that under 0-1 loss. You can also now write the risk minimizer in a slightly different form for the binary case. So for the binary case, we can write this in terms of these conditional probabilities. So we would say if the conditional probability is above 50%, we would say class 1, and if it's below 50%, we'd say class 0. But that's just us, again, picking the most probable class and writing this down slightly differently for the important case of binary classification. And again, there's a nice little short and compact formula, which I've again written now in this eta thing here, which are our conditional probabilities for x. So you can also write it like that, and you can like directly work with this as the error rate for 0-1 classification. I want to wrap things up by showing a very, very simple and short example for the base classifier and the base error rate. So as always, I'm trying to visualize things and I guess I'm not simulating much here, I'm mainly visualizing. And while I did that, I figured out that I could maybe add in a few comments on generative classifiers. Okay, so let's do this. So, like I said, what we're doing is at every point x, we are doing this argmax here of these conditional probabilities, and so we just predict the most probable class. That's already, so there's nothing new in that regard, so I'm just copying that over from the slides before. So let's assume that we actually have some way of modeling these conditional probabilities here. Well, actually, let's not assume that. Let's assume that we can model densities given classes. So let's assume that I can model this here, because this is often what we can do in these, or this is exactly what we are doing in these generative classification approaches. So assuming you're in class 1, you're in class 2, how is your feature vector distributed? So maybe it's, I don't know, some Gaussian distribution or something else, okay? And you're willing to make that assumption. Now, if you want to get your hands on this guy here, on these posterior probabilities, which is what you likely want, if you're doing predictive modeling, probabilistic modeling, you can simply use Bayes' formula. And we've also looked at this before because I already introduced things like LDA and QDA and so on here in this lecture in a different chapter. So we can use Bayes' formula and look at this thing here. And the idea is that we can model that. These are our prior probabilities for our classes, and these are really easy to estimate. So we just have to count proportions. I'll also discuss this here. And this here is pretty much just a normalizing constant. So if we're just looking for the optimal prediction or the optimal parameter vector, well, we don't really care about that. So in terms of maximizing things, or picking the class which is which comes or with maximal posterior probability, we could just say, let's maximize this thing here. Yeah. So, and if you have a model for this, and this we can always easily model by looking at our data, we can also pick the optimal class from that instead of looking at this. Yeah. So we can estimate these conditional densities now. We can estimate the prior props, and then we can use them for classification. Cost optimal classification. So, well, 0-1 loss optimal classification, I guess I should say. And you can actually see that because generative approaches in classification really work like that, if you then maximize this thing here, which is what you're going to do in these generative approaches, you are doing the optimal classification under 0-1 loss. Okay, that's nice. That's kind of another thing we are now understanding here. And like I said, you will see exactly this idea in linear discriminant analysis, quadratic discriminant analysis, MDA, and that's a whole bunch of these variants of discriminant analyses. And I don't want to take this way further here, so I just did a super simple example here. So I assume that my prior probabilities are 50-50. I guess I'm also assuming that there are two classes, a positive, a negative one, a 0, 1. Is, maybe I shouldn't say 0, 1. Super confusing, a class 0 and a class 1. And I'm being extremely lazy here and simplifying things a lot. So I'm just saying, hey, my feature vector is univariate. I'm assuming everything is normally distributed in these classes. And there's pretty much a standard Gaussian going on in both of these classes. And I've plotted these two class conditional densities down here below. And because the prior probabilities are the same, it's very easy now to identify the points in X space where a certain class wins. For that, you simply have to compare these two densities. So I guess, I'm not super sure about this, but maybe I am. So this here should be class 0. And yeah, this here is class 1. And if I want to figure out whether I should predict class 1, normally I would have to multiply the density with the prior probability, right? Which I don't have to do here because they are both the same, so I can forget about them. So the only thing I have to do is I have to figure out whether my density of class 0, which is this, I don't know, purplish thing here, is larger than the density of the other class. And on the left-hand side of this orange threshold here, that's exactly the case. So here I would say class 0. And on the right-hand side, this thing here, this greenish bell curve, is above the purplish bell curve. So here I would say class 1. So in this case, my threshold exactly at the 0 point, which is, I guess, what one would naturally assume that this would happen. The other thing is we can also now talk about what the base error rate is. And the base error rate is exactly this reddish area here. So for example, if we would be in in a certain feature region, so here, say here, then this, like assuming we're in that feature region, that's here the probability of us being wrong, right? Because there are some points which are sampled here from this greenish bell curve, but we're still saying it's class 0. So it comes from this purplish bell curve. And then this area here, that's exactly the error we are making. And if we integrate that out, over the whole feature space, then this red area is exactly what is like under the wrong bell curve, so to speak. And you can analytically now determine here the base error. That's actually maybe a nice exercise. Actually do this. This is actually a good homework exercise. Maybe take this example here, write it down mathematically, insert the formulas for the base error rate, and compute these. This integral over mispredicting the class, so to speak, and see whether you can actually get your hands on a resulting value and resulting formula. And small hint, this is indeed possible and not that hard. And you can even do this for multivariate normal distributions and so on. I've done this before in other parts of the lecture and certain simulation examples. Okay, I'll stop here. I hope you enjoyed this. I hope you learned something. See you in the next session.